Hey there, in this video we are exploring problem solving with recursion in C++ programming, and this covers sections 19.4 to 19.10 in the Gaddis textbook. So in the prior video, which hopefully you watched already, we gave a short introduction to the basic idea of recursion of a function that calls itself and getting repetitions done in a way that doesn't use loops. In order to make one of those functions actually work for us, we need two parts to it, and we need a base case, which is very simple, and a recursive case, which does a little bit of work, and then calls the function again with a smaller version of the same kind of problem, basically. And saw a couple of very simple examples there. Saw a factorial function that's recursive, saw a function for GCDs, greatest common divisors. And those are two, canonical, common examples when you first start seeing recursion. But, they're still a little bit silly because they're things you could totally do with a for loop, frankly, and you don't really need recursion for that stuff. But in this video, we're going to see some examples where you really do want recursion. It's very much the easiest way to do these kinds of jobs. But I'm glad you saw the other video first to just get an idea of what recursion is. Let's get some real work done here. Okay, so here I'm going to be thinking about recursively defined structures. And what does that mean? A recursively defined structure is a structure whose definition refers back to itself. And when I say structure, I mean some kind of data structure. It could be a literal struct. It could be a class here in C++. Other languages use other terminology. But a data structure whose definition refers back to itself. And so examples of this would be a linked list, a dynamic stack, a dynamic queue, any one of our abstract data types where the nodes include pointers to other nodes, right? The linked list is your primary example of that. And what you're going to see in this video is we're going to be working on an example that we first saw back in chapter 17. There's this number list class that stores a bunch of doubles, as many as you like, right? It's a linked list. And so the primary unit that it's got is it has an internal private structure called the list node that's got one single double for the data and a pointer to another list node structure. And so you might want to go back and review that. But here in chapter 19, we have basically the same class with a couple extra stuff added to it. And so, even now, I look at that class and I say, how did, it's kind of surprising that the list node structure can contain a pointer to a list node structure when that is the structure that you're currently defining in the code. So I'm still kind of surprised that works, but it does. Not every language in the world permits that, but C++ does. And that's a great example of a recursively defined structure whose definition refers back to itself. And that's exactly the kind of thing that recursive functions work super well with. And that's what you're going to see here. Now, there's a couple of other reminders. Again, back in chapter 17, remember that the linked list works by chaining together a bunch of those kinds of list nodes. And at the end, the pointer at the end has null pointer for a value. That's the sentinel back at the end. So, maybe pause the video and go back and review that in chapter 17 or look at the revised version here in chapter 19. And all of our examples in this video are talking about that. Okay, so we're going to add a function. We're going to add a function to that number list class. And we want this function to count the number of nodes in the linked list. Now that's the kind of job that's super easy for arrays. I mean, obviously you just have an integer storing the number of things in your array or your partially filled array. That's trivial. But we never had that in our linked list class back in chapter 17. We should totally add that. Well, this is the kind of thing that you really want a recursive function for. So think through the recursive design. We're going to write a function to count the nodes in the linked list. It's going to take a parameter, and that parameter is going to be a node pointer, a pointer to a list node. Okay, now here's the recursive case, which is usually the tricky part. The recursive case is I'm going to count 1 plus a count of the rest of the list. Okay, so whatever a node I'm currently in, that counts for 1. And then I'm going to recursively call the function that we're making right now with the next pointer and just say, hey, count all the rest of the stuff in the list from the next node on. Okay? That ought to be it. That ought to be the number of things in the whole list. And of course, we need the base case, and the base case is the pointer that you pass into this function is null pointer, then return 0 because you're not actually looking at any nodes at that point. Let's look at an illustration of that. Okay, so I'll have a linked list like this with a bunch of nodes, and right now I don't know how far it goes on. So the function that we're designing here, I'm going to pass in this pointer to the first node in this picture. So I'm going to count that as 1, obviously, and to that 1 I need to add a count of the rest of the list. How's that going to work? Well, I'm going to take the next pointer and just pass that into the function that we're talking about. So, the C++ is going to take care of all that recursive stuff, but, think about whether this makes sense. And so as you usually say, this is kind of a big idea, a different way of thinking about computing. So if you like, maybe pause the video, kind of meditate on this picture and think, does this make sense that that would be the right answer? Right? Assuming that the recursive function just takes care of the complexity for us, would that be the right answer? If I did 1 plus a count of the rest of the list, would that actually be correct? And when you're comfortable with that idea, restart the video. We'll see what it looks like in C++ on the next slide. All right, here's the function. As usual, remarkably short. So we have this function in the number list class. It's called count nodes, and in comes a list node pointer that we're calling node pointer here. It's a const function because this function is just counting stuff. It's not changing anything in the list. And just like we said, here's the base case. I'm sorry, actually they tricked me. They wrote this in the other order. Here, the if statement's the recursive case. And you know what? Actually, I kind of like this better because usually, like I've said, when I'm designing recursive functions, I want to think about the recursive case first because that's the one that's hard to get right. So I actually kind of prefer this myself. So the recursive case comes first. If the node pointer is not equal to the null pointer, then do like we said, return 1 plus a count of the nodes from the next node on. So this node that I'm currently in, which is node pointer, right, dig up the next pointer. Here's the recursive function called count nodes with that next pointer. Great. That's it. That's the number of things, right? Otherwise, here's the base case second now, return 0 if you did get the null pointer. Now, one little detail on line 196, there's another way of writing that if statement. Some people would just write that as just if node pointer. End of story. Because remember, the null pointer is really 0. So if node pointer is anything else, then it must be some positive value, and C++ would count that as true, and you get to line 197. Whereas if the node pointer is null pointer, which is really 0, that's just false, and that would definitely send you down to line 199. That's probably how I would write it shorter, but some people find this, more clear for readability purposes, but I would just write that as if node pointer. That's all you need. And again, you're adding up 1 for the node you're currently looking at, getting the next pointer, and of course what happens is when you call count nodes recursively, that counts 1 for that pointer plus a count of the rest of the list from that point on with that pointer. And it calls it again, and it calls it again, and it calls it again, and you're really adding 1 for every single node, and then 0 at the end when you hit the null pointer, and all those ones get added up, and that actually is the right answer. Again, remarkably short there. Now, another little detail you're seeing on the bottom of the slide here is that function there has to be private because it's talking about list nodes. And if you go look at the code in the book again, list nodes are private. They're defined in the private part of the class, and the application programmer doesn't have access to them, and the application programmer should not have access to them because that is a detail that should be internal to the class. And, linked lists are a little bit complicated. The application programmer should not worry about that stuff. So this function has to be private. And in order for there to be some function for the application programmer to use, we have this second public function that's just called num nodes, doesn't take any parameters at all. And that's just a one-line function there where it calls this count nodes with the head pointer, which hopefully remember is the first pointer at the lead of the list That's how the number list class actually works. That's how any linked list is going to work. So you have this initial triggering function, I would say. This one's public, and the application program would call my object.numNodes. This kicks off the recursion with the very first pointer, and then it recursively calls itself and itself and itself and itself and itself until you hit the null pointer and you get the right answer. Neat. Super neat. Again, super short function. Very readable once you wrap your head around how the recursion works. And that totally works. Nifty. Let's look at another example. Okay, so let's say you wanted to print out your list in reverse order, right? I mean, obviously forward order is easy. You just, do your standard list traversal and print out everything in order. What if you wanted to print it out in reverse order? Okay, so once again, you're going to see a function that takes a parameter that's a node pointer, right? Starting with the head of the list. I'm sure the first time it gets called. So take a node pointer just like that last slide. And thinking about the recursive case, right? This is the tricky part. But on the other hand, recursive function calls once you wrap your head around, they're very, very simple idea. So recursive case here is print the rest of the list, right? Whatever node I'm in, print the rest of the list reversed from the next node on. And then once you're done with that, print this node. Great. And in the base case, again, very simple. If the pointer is null pointer, then don't do anything because you're looking at something that's not really a node at all back at the end of the list. That's it, right? That's the basic idea. Let's look at an illustration of that design. So once again, I have a linked list here, okay? The function that we're creating that we're going to see in code on the next slide, you pass in a pointer to it, all right? And the first thing you're going to do is you're going to get the next pointer and you're going to ask this function that we're talking about to display the rest of the list reversed. And I'm just going to assume that that happens magically. Okay, so again, the very last thing on the list it shows up on screen first, and the one before that is second, and the one before that is third, et cetera, et cetera. That job's all done. So all the other stuff got printed in reverse order. And then, once that's done, print this node, right? And of course, this node's actually the first node in the list, but we're going to print it last, and now you're seeing the whole list printed in reverse. That's it. That's it. Very simple idea, right? Once you know that you have recursion available to you, you can just say, hey, do this job in this function I'm talking about with one piece of less work. So the basic idea is print the rest of the list in reverse order and then print this node. So once again, right, if that seems shocking that that idea would work, pause the video, kind of meditate on that, think about whether that would actually be correct. And then when you're ready, restart the video and we'll see the code on the next screen. There we go. As usual, recursive functions are ridiculously short. So here we are in the number list class, and we have this function called showReverse, and it takes a list node pointer called node pointer. And once again, here is the recursive case in the if statement. So once again, as long as the node pointer is not equal to null pointer, could have written that as just if node pointer, however you want to write that. Here's the recursive case. Call this function recursively, show in reverse the rest of the list from the next pointer on, right? We're in this node pointer, right? Dig up the next pointer and just pass that into show reverse, and that takes care of the rest of the list. And once that's done, print out the value in this node. That's it. You don't even need an else part, because what we said on the prior slide is if you are dealing with a null pointer, don't do anything. Okay, well, I mean, don't do anything. You don't need an else part for that. That's it. You literally, in this case, you just have the recursive case. How amazing is that? That's it. 3 lines. Awesome. Now, once again, this has to be private because it is referencing list node pointers, and those were defined in the private part of the class. Again, the application programmer cannot have access to that. So once again, we need a public function that the application programmer is going to use to trigger this process. So you're going to see this display backwards function that's public, if you look at the code in the book, takes no parameters, and very similar to the last one, it just triggers the beginning of the recursion by calling show reverse here with the head pointer. And that starts it off in a recursive call, recursive call, recursive call, all the way to the end of the list. And then it actually literally does all the printing backwards because of the call stack, right? Really what happens here when this works is every single list node pointer gets added to the call stack. And then as you start popping, right, the last thing that was put in is the first thing that gets printed. And the thing right before that's the second thing that's printed, right? And it's exactly how the call stack works that causes things to get printed out in reverse. That's exactly what you want. How great is that? Okay, so let's take this for a test drive. I've gone into the Gaddis lecture code. This is program 19.8 that we're looking at specifically to test out the show reverse function that we just added. And this is a multi-file program, so I had to go get numberlist.h and numberlist.cpp, that's the object we're testing, as well as the test driver, program 19.8 here, put it into a dev C++ project, as you'd expect. And if you want to see what's in that numberlist class at this point, right, the couple things that have been added to it in chapter 19, you can look at the classes tab over here. And you have all the old stuff we talked about previously. There's append node and delete node and insert node and the constructors, of course. There's display list that just traverses it in forward order and prints everything. But the new stuff we've added is, of course, count nodes, that's a private recursive function, and num nodes, which is the public thing. And what we're testing right here is the private show reverse recursive function. But of course, in this program, the only thing we're going to have access to as the application programmer is display backwards. So you can see here that, of course, we make a numberlist object called list. Going to add some data to it with the append node function. And so the way this for loop is working, increments by 1.1, you're going to add 1.5 and 2.6 and 3.7 and so on and so forth, as long as it's less than 10. And then we'll do list.displaylist and see everything in the forward order. And then the really critical thing down here on line 24 is called list.displayBackwards, and hopefully that shows everything in reverse order. So we should be able to compile it. Great, there's my executable, and we should be able to run it. And there's the result. So the forward order, of course, 1.5, 2.6, 3.7, et cetera, et cetera. I guess there's 8 things there. 1, 2, 3, 4, 5, 6, 7, 8 things, right? And then here is our call to display backwards. And sure enough, you see the 9.2, 8.17 at the start here, all the way down to 1.5, which is actually the very first thing in the list. That totally works. Neat. Now, let's see if we can do a little bit better. So this is not something you normally worry about when you're working in a high-level language like C++. But let's go and dig into the actual code that's doing that way down here. This is all old stuff from chapter 17 that we're looking at right now. But the stuff that we just added here is this, here's count nodes, and here's show reverse, which is what we added in this video here. Just exactly like we saw in the lecture. How incredibly short is that? So I'll put a breakpoint right here, and I'm going to start debugging that same program. Okay, so program's currently running, and it's we added the data, and we've got the display in forward order, and now we're waiting to print stuff in reverse order. And I'm going to pull up, as we've done a couple times, I'm going to pull up the CPU window and see what's really going on in the guts of the system. Over here on the right, of course, are the CPU registers. We're not too worried about that at the moment. Up here on top is the assembly language version of this same code. And again, we're going to leave that off for your computer architecture course. But the thing I'm really interested in right now is what's sitting in the call stack. So hopefully I can get all this stuff visible at once. There you go. So at this point, of course, we called the main function to begin with. And in the main function, you had the call to the public function display backwards. And then the display backwards function called the private function show reverse and passed in the head pointer. So apparently, on this particular run of the program, the head pointer is this pointer hexadecimal CC12CO is where the starting node is in the list. Now remember, for all of these instance member functions, there's also the this pointer to the object you're inside of that's getting passed in invisibly automatically. So apparently the list object is at address hexadecimal 7AFE9C, and you're going to see that as part of all these function calls. But I'm really interested in this node pointer. Okay, this node pointer is the head of the list. That's actually the pointer to the first list node in this list. But you get in this function on line 210, and obviously that node pointer is not null pointer. Remember, null pointer is actually 0. That's not that. So you're going to go into this if block, and you're going to call show reverse again with the next pointer. So I'm in the first node, and the first node has a value, of course, and it also has a next pointer. And so what we're doing is digging up that next pointer and calling show reverse with that next pointer, which is really pointing to the second node. So as you should be able to expect now, as we go into this function, a new stack frame shows up, right? And this is the one where you passed in the pointer to what's really the second node. And that's not null, so you're going to call show reverse with what's really the third node, right? And you add the next pointer, and you add the next pointer, and the next one, and the next one, and the next one. Okay, now there's the null pointer that just showed up. So for what it's worth, at this point, we actually have all 8 pointers, right? There's 8 things here. 1, 2, 3, 4, 5, 6, 7, 8, right? Those actually are the pointers to all 8 nodes in the list. And then right at the end, we added the null pointer up there on the stack, right? That's the end of the list, obviously. And now on line 210, that's false because the node pointer actually is the null pointer. And now for the first time, you're not going to get in this if block. You're not going to have a recursive function call. You're going to start coming out of the function, right? And let's think about what happens now. So obviously you come out of the function and you pop the call stack, and that goes away. Okay, that sends you back to line 213 now. And what's going to happen is this pointer here, which is actually the pointer to the last thing in the list, you're going to go find that thing's value. You're going to print it to the screen. That's the first one that shows up. Hopefully that's clear. So that last thing, you're entering the printing statement here. You see that in call stack right there, right? And that calls this here, which is a different function. And that's how the 9.2 gets on the screen, on the console there. And now this version of the function is wrapping up. And as that happens, you're going to pop this, you're going to pop the top frame off the call stack. And now you're in the version with this pointer, which is actually the second to last thing. And you go look at that value and print that value to the screen. And you're in the printing function. And there's the 8.1. Right? So just the natural way that a stack works, right? Again, a LIFO data structure. The last thing in the list that got added in, that's the first thing that comes out and gets printed. And that just magically happens because that's how stacks work. How great is that? So you get the next one, and you get the next one, and the next one, right? As the stack, call stack unwinds, some of us say, right? And you're printing this last one, and you can see you got 9.2, 8.1, 7, 5.9, 4.8, 3.7, 2.6. Right, there's one more to go here. Hopefully we see that. And you're coming out of that. Great, and now you're in the main function, and you see all of them on the screen. Fantastic, fantastic. So, interesting, deep call stack, the way that works. You might think about, do I really want all that information on the call stack? I mean, it's only 8 things, that's perfectly fine. But for larger things, you might want to be aware about exactly what's happening there. And of course, we'll pop the main off the call stack here as we get out of this function. And then the program sends you back to Windows, and you're actually done. Interesting. So again, hopefully that gives you a little primer of the things you might want to be keeping in mind in your computer architecture course as you dig into the specifics more about how the CPU is working and how the memory is working with the call stack and stuff like that in your future courses. But admittedly, again, when you're working as a high-level language programmer from C++, you don't worry about all those details. You just say recursion works, and I can design a recursive function that does one little piece of work, like prints one node, and just calls the function to do the rest of the job. And that does the rest of the story, you might say, and it works. And that's really kind of the mind frame you're working in at the high-level language of C++ or C or Java or something like that. Recursion fundamentally works, and the system just takes care of the rest of the stuff. And that's awesome. Okay, one more example. Boy, I feel like this feels important. The quicksort algorithm. Back in chapter 8, we started looking at sorting algorithms like bubble sort and selection sort. And we said, yeah, they're pretty good. And we said, we're going to be on the lookout for things that are maybe even better in the future. Well, now's the future. So the quicksort algorithm is an algorithm that was invented in 1959 by Tony Hoare, who still gives lectures on this once in a while, up until recently. And this is a recursive algorithm, which is why we couldn't talk about this until chapter 19, that can sort either an array or a linked list. Actually, that feels important. Our prior algorithms were only designed for arrays. And I feel like if you try to use a selection sort and you use that on a linked list, it's going to work very poorly, frankly. But this is a sorting algorithm that will actually work for either type of data structure that we're talking about, arrays or a linked list. And the basic idea is first of all, it determines an element or a node maybe somewhere. I mean, it kind of doesn't really matter where, maybe in the middle, could be elsewhere, called the pivot value. And we're going to consider all the stuff that comes before it, we'll call that sublist 1, and all the stuff that comes after it is sublist 2. Either whether this is array again, or it could be a linked list, doesn't really matter. And then what happens is, having determined that pivot value, here's where the magic is, the values are shifted so that, maybe a little bit, so that all the elements in sublist 1 are all less than the pivot value, and all the stuff in sublist 2 are all more than the pivot value. Now, that having been said, they don't have to be ordered. So, for example, if the pivot value is 50, maybe sublist 1 is 10, 40, 20, 30. Could be. And then sublist 2, remember, the pivot value is 50. Maybe sublist 2 is 60, 100, 70, 90, 80. Something like that. And if you dig into the details, it usually doesn't take much work to get in that situation. If you don't care about the ordering of sublist 1 and sublist 2, you only usually need to swap like 1 or 2 or 3 or a very small number of things to get it stacked up according to that definition. It doesn't take very much work at all to make that happen. And then the recursive case is this function we're talking about, just pass in sublist 1 to it and pass in sublist 2 to it. Okay, and then it does the same kind of job. It gets a little bit more ordered on each call. Now the base case, of course, is that in this function, if you pass in an array or list of size 1, don't do anything because one thing all by itself counts as being in order. Hopefully that's obvious. All right, so we're not going to look at all the code here in this video. We don't have time for this, but an incredibly important algorithm. I'm so glad that Tony Hoare invented this because, and feel free to look at the specifics in the Gaddis book for how this works, is that it turns out this is much faster than the other sorting algorithms that we looked at in chapter 8. And the details are that, we may have talked about this earlier, both bubble sort and selection sort, ultimately, they have these double nested loops, these 2 loops. And if you count up the maximum number of times that they happen, they both, if you have an array of size n, they both can happen up to n squared steps worth, up to n squared iterations for a size n array. Well, the quicksort algorithm, if you have a size n array or list, it's only going to have a number of steps, which is n times the logarithm base 2 of n, which is a much smaller number. And if maybe you might know in computer science in later courses, we talk about big O notation, which is how you measure the speed or the amount of time that an algorithm takes. And so the prior sorting algorithms were big O of n squared. That's the number of steps they could take. And this here is big O of n times log n, a much smaller number. This is as fast as a sorting algorithm can get. That's important. And it works because it's recursive. Awesome. So feel free to look at that book. There's a lot more details there, but make a long story short, the fastest sorting algorithm in the universe, provably so, there can't be anything faster than this, uses recursion. Super clever. Okay, so let's kind of summarize recursion versus iteration, right? Your 2 primary ways of getting repetitions done in a programming language. So recursion has a lot of advantages here. It models some algorithms more accurately. Frequently, what we wrote down in the English or the math is almost exactly what we wound up writing in the function in code. it syncs up super nice with recursively defined structures. So if I am working on a linked list or a dynamic stack or a dynamic queue or something like that, it's probably going to be most straightforward, like the examples we saw here in this video of using a recursive function. I would not have wanted to do the count things in a list or print out a list in reverse order using a loop. Much more straightforward using recursion. And you'll continue to see that in the future. It usually results in shorter, simpler functions. We've kind of emphasized that a number of times. And I don't know, maybe this is more important than all that stuff, but it comes in a future course. It supports proofs of correctness and complexity. So when you get into future computer science courses, like maybe your discrete mathematics course, which is where you start proving correctness and complexity and stuff like that, it might be really important to be able to write your functions recursively. And as one example, in the program where I teach our discrete mathematics course, which is CS 3500, we use this textbook by Rosen. It's called Discrete Mathematics by Rosen. In Chapter 8, specifically Section 8.3, there's a big theorem called the master theorem. That's what it's called. When you want to measure the time of an algorithm, here's a theorem that answers it all. You just look it up, and here's how much time your algorithm will take to do. But it assumes that you wrote the function recursively, right? In order to use the master theorem and figure out how much time your algorithm takes, you need to write it recursively. And if you're proving that the function is correct all the time, again, for a lot of reasons, it's easier to have a recursive function than iteration. Okay, so that's a future story. That's a big future story that you'll see in the future in other computer science classes, I bet. Now, iteration, right? A for loop or a while loop. I mean, it's not terrible. There's some advantages there. If you're using a for loop or a while loop, you avoid pushing lots of data to the call stack, right? That was kind of critical. Recursion does push lots and lots of data to the call stack. Maybe you don't have that much memory available, possibly. And in many cases, iteration will be faster. It's using less memory, and instead of doing, function call, push a bunch of data, function call, push a bunch of data, maybe just using one variable for your for loop was actually faster. So traditionally, we usually say that iteration tends to be faster, right? Again, that's what Alan Perlis said. We're trading description for time. So recursion, shorter function, usually takes more time. But, we have the example of the quicksort, where the quicksort algorithm actually is the fastest sorting algorithm in the universe. And it uses recursion. So, not always the case. Interesting. Okay, so that is the end of our very brief introduction into recursion here in Chapter 19. So if you want to really fully understand that, I would recommend you read the Gaddis book, Chapter 19, see some other details. Test yourself with the review questions at the end of the chapter there. Now, my students, I'm sure, will be getting ready for their final exam here in the second semester of their Starter C++ programming course. So I would recommend to my students go on the learning management system, look at the practice final exam that does cover everything we talked about in second semester. And of course, in order to accomplish that stuff, you need to know everything we talked about in the entire year of C++ programming. So you do need to have all that stuff available at your fingertips for our final exam. And then you're going to be ready for the future courses like assembly language or discrete math or stuff where you talk about these other issues. Now, again, if you want to really get good at recursion and get a head start on those future courses and get comfortable with that technique, I would recommend these programming challenges here, 19.4, 19.6, 19.7. They're all really short. I mean, they're all really short little recursive functions, as you do. But you probably want to think about it, and the more practice you get at that, the more comfortable you'll feel about it in those future courses when you do use them. Okay, and here's the lab I would do with my students. There's this programming challenge 1910 here, which asks you to take that number list class, add another new function that's something that you would probably want, a max node function, a function that gets the biggest value in the list. Again, think about how we design those functions in this video here. It's going to be a function that takes a pointer, and there'll be one private version that's recursive. There'll be a public version that kicks it off. But really thinking about the private recursive version, takes a list node pointer. how do you find the biggest thing, the biggest value in the whole list, right? And there'll be a base case, there'll be a recursive case. The recursive case is the interesting part. And here's a hint. I'll just give you the base case right now. For an empty list, right, if you pass in the null pointer is what I'm saying, for an empty list, return the defined value negative infinity from the C math library. So there's this special code, the way that doubles are stored. There's a special code for positive infinity and negative infinity. And so I'm recommending for an empty list, just send this back, because then if you compare that to any other number, obviously the other number is bigger. So I'm just looking for something that anything else is bigger than. So that's what I would do in that case. And there's your base case right there. And then all you have to do is think about the recursive case, right? And what you're allowed to do is you're allowed to use comparisons like lesser or greater or equal to, and a call to the function that you're inside right now. So think about that. So that's a pretty good lab. So I'll think about that with my students. And again, you don't really need the book for this. You can just do this on your own. I guess you do need the numberless class to begin with. I guess you do need the book code for that. So hopefully you do have access to that. Or you can just write your own linked list, right? Just write your own linked list from scratch. I mean, that's a good exercise to get ready for your next data structures class. And what a great exercise that'll be. So think it through, right? Once you get the idea, it's going to be a pretty short function as usual. Add that to your linked list class. So there's another chapter in this version of the book, and in the next video, we're going to briefly address that last chapter 20 on binary trees. Now, that's another abstract data type, in addition to other stuff. And among the things we've talked about in the past, there's certain advantages to arrays. You can jump into it. You can, do a binary search to it very fast. That's all great. There's a bunch of advantages to linked lists. It's recursive. You can add stuff to it. Wouldn't it be nice if there was a data structure that kind of had the advantages of both at the same time? And that's the story of binary trees. But we couldn't get to it until now because everything about it is all recursive. And put that together and you actually get kind of the advantages of everything all together. That's important, and that's going to be the last part of the book that we'll cover in the next video. So I'll see you for that.